Hello, welcome to my video for lesson 3.3. This video is intended to help you learn about standardization and using the standard normal tables at the back of our book. Standard normal distribution is a normal distribution that has a mean mu equal to 0 and a variance sigma squared equal to 1. And we use the notation z to indicate that a random variable has a standard normal distribution. There are two different tables in the back of our book in Appendix B that show the standard normal distribution and can be used to find probabilities and percentiles for standard normal distributions. The first one is Table 5A, which is shown, part of it is shown here. And it gives us the area to the left of a cutoff value. So if we have the probability that z is less than 0.53, we find in the left-hand column, we find 0.5. As we go across the columns, we find the column that corresponds to 0.03, so that would be 0.53. And where they intersect gives us the probability. So the probability that z is less than 0.53 is 0.7019. Now, if we want to find the probability that z is less than 0.53, we don't see any negative values for z here in the table, but we are told that we can use the symmetry in the standard normal distribution, and that the probability that z is less than a negative z value is 1 minus the probability that our standard normal is less than our positive of that same value. So for instance, the probability that z is less than negative 0.53 is going to be 1 minus the probability that z is less than 0.53. And we saw that our probability that z is less than 0.53 is 0.7019. So if we do that subtraction, we find that the probability that z is less than negative 0.53 is 0.2981. Now let's look at how we can find a percentile by looking up the 75th percentile. So now, instead of looking for a z value, we're going to look in the body of the table for a probability equal to 0.75, because that's going to be the area below for the 75th percentile. We can see that that falls in between these two values that are highlighted in the table, the 0.7486 and the 0.7517. And if we look at the z values that those correspond to, we can see that our 75th percentile is going to have to be between 0.67 and 0.68. So we'll take the midpoint between those numbers and estimate our 75th percentile as 0.0675. Sorry, 0.675. The other standard normal table in Appendix B, Table 5B, instead of showing the area to the left of the cutoff value z, it shows us the area to the right of the cutoff value z. So if we want to find the probability that our random variable z takes on the value greater than 0.69, we find the row corresponding to the 0.6, the column corresponding to the 0.09. They intersect at the value 0.2451, so that is our answer. If we want to do something a little more complicated, find the probability that our random variable z takes on a value between 0.1 and 0.6, what we can do is we are going to need this area under the curve between 0.1 and 0.6. We're going to take the area above 0.1 and subtract the area above 0.6, and that's going to give us our answer. So we use the table to find the area above 0.1. That's 0.4602. The area above 0.6, 0.2743, and the difference is our answer, 0.1859. And then the last thing we're going to do is look at how we can use this table to find a percentile. We'll look for the 80th percentile. The 80th percentile will have 80% to the left, which means it's going to have 20% in that upper tail. So we're looking in the body of the table for 0.2000. And we can see that it's between these two values of 0.2005 and 0.1977, which means that our 80th percentile, if we go and look at the z values that correspond to those, our 80th percentile is going to be between 0.84 and 0.85. So we'll take the midpoint and say our 80th percentile is about 0.845. These values can also be found with a calculator. If you've taken other statistics courses, you may have used the TI 83 or 84 with the normal CDF and the inverse normal to find these probabilities and percentiles. Either way is acceptable. Okay, so now let's move beyond standard normal and say, okay, well, suppose that x is any random variable that follows a normal distribution with a mean mu not necessarily equal to 0 and variance sigma squared not necessarily equal to 1. And here's our notation for that. Now, if we subtract the mean from x, we are shifting this random variable so that it's going to have a mean of 0. And if we then divide by the standard deviation, square root of sigma squared, or sigma, we are forcing the standard deviation of this random variable to be 1, which would mean that the variance, 1 squared, is still going to be 1. And that's going to give us a random variable, which we'll call z, that is going to have a standard normal distribution as long as x has a normal distribution. This is only true because we started with a random variable that had a normal distribution. If we started with a random variable that did not have a normal distribution, this z would not be normally distributed. And just a reminder, this is our standard normal. So this gives us a way that we can use the standard normal tables to find probabilities for other normal distributions. Let's see how. Suppose that x is a random variable that corresponds to IQ test score, and that the distribution of IQ test scores is normal with a mean of 100 and a variance of 225. If we want to find the probability that an individual will test with a score greater than 120, we're going to transform both x and the 120 into a z. So we're going to subtract off the mean and divide by the standard deviation for both of them. And this is going to be equivalent to finding the answer to the question, okay, what's the probability that x is greater than 120? Well, it's going to be the same as the probability that a standard normal random variable takes on a value greater than 1.33. We can go to the table to answer this question. So here, we're looking for the probability that z is greater than 1.33. So table 5b is going to be useful here because it gives us the area in the upper tail. I look at the row with the 1.3, the column with the 0.03, and I can see that my answer here is 0.0918. What if I want the probability that my random variable, my IQ test score, for a randomly selected person is less than 90? Again, I'm going to transform these by standardizing, subtract the mean, 100, divide by the standard deviation, which is the square root of that variance. So I'm going to be able to find the probability that x is less than 90 by using the probability that a standard normal random variable is less than negative 0.67. Using the table, I'm going to use table 5a this time because that gives me areas in the lower tails. I know that I can find this probability by taking 1 minus the probability that z is less than 0.67. I find 0.67 in my table. So that's 1 minus 0.7486, which gives me a probability of 0.2514. Now, if I want to find the probability that a test score is going to be between 90 and 120, that's in this region here, I can use the fact that I know the probability that x is greater than 120 is 0.0918. I found that earlier. The probability that x is less than 90 is 0.2514. I found that earlier. And I know that the total area under the curve has to sum to 1. So I can find the probability that x takes on a value between 90 and 120 by taking 1 minus those other two areas, which gives me 0.6568. Finally, let's see how we can find a percentile using another portion of the table. We already did it using the body of the table, but there is another part of the table for us to look at. I'm going to look at how high a score would need to be in order to be in the top 5%. We're going to do this by finding the value on the z-table with 5% in the upper tail. So we're going to use, finding the top 5%, we're going to use this portion of the table down here. In the alpha row there, that gives us the percent in the upper tail that we're looking for. So we are going to be able to look in the 5% column, and we can see that the value that's going to cut off 5% in the upper tail is 1.645. So the value on the z-table that has 5% in the upper tail is 1.645. Now we're going to need to transform this back into an IQ test score, our x random variable. We know that our z is equal to x minus the mean divided by the standard deviation. If we manipulate this, we can calculate x by taking the mean plus the z value that we found in the table times the standard deviation. There's our z value, 1.645. So we're going to solve for x. X is equal to our mean, 100, plus our z value, 1.645, times our standard deviation, which is the square root of 225. And that gives us a score of 124.675. Hopefully these calculations are somewhat familiar. If you have any questions about how to use the tables, please let me know, and have a good day.